These are the notes for AP Calculus on the topic of inverse trigonometric functions and differentiation. So let's first review what these inverse trig functions are. Remember that inverse is written with this arc in front of it, is one way of writing it. So if you have the arc sine of x, that reverses sine of x. So this is saying if you plug in some angle here, let's say into sine, and take that result and plug in the arc sine, then it reverses it, gives you back the angle, whatever that is, x. Or if you do it the other way around, if you plug some value into arc sine and take the sine of that, again, these are inverses, they reverse each other, so you get back what you started with, x, either way. But let's first look at the range or output of these inverse trig functions. Because in order to be functions, remember, you can only, for every input, you can only have one output. So these are the graphs of the original trig functions here. They go with the inverses above them. So arc sine, arc tangent, and arc cosecants have ranges between negative pi over 2 and pi over 2. Because if you look at their graphs there, of sine between negative pi over 2 and pi over 2, tangent with the asymptotes here between negative pi over 2 and pi over 2, and cosecant between negative pi over 2 and pi over 2. On those intervals, you can see if we restrict the domain here, we don't get any repeated values on these intervals, which means there won't be any repeats on the range of the inverse. Or another way of looking at it, remember, you can apply the horizontal line test to these functions. These, on these intervals, would all pass the horizontal line test. The horizontal line would only pass through once. But if we draw it any further, beyond those intervals, let's say like this, then it wouldn't pass the horizontal line test. It would be two different values, and that would mean there'd be two different answers for the range here, which would make these inverses not functions. So that's why these are restricted between negative pi over 2 and pi over 2. Or another way of looking at it, on the unit circle, you're looking on these between negative pi over 2, which is right here, and pi over 2 right here, in the first and fourth quadrants, or zeros right here. So if it's positive, you're going to be looking, if you're substituting something in positive, you're going to be looking in this first quadrant, and negative, you're going to be looking in the fourth quadrant, between negative pi over 2 and 0. However, the other three trig functions, they pass the horizontal line test on a different interval. So these are the original graphs of cosine, cotangent, and secant between 0 and pi. These graphs also pass the horizontal line test. So that means their inverses, arc cosine, arc cotangent, arc cosecant, would have ranges that correspond to the domains of the original functions between 0 and pi. So for these three, we're going to be looking between 0 and pi. So either in the first or second quadrant on the unit circle. Again, if it's positive, we're going to be looking in the first quadrant again. Negative this time in the second quadrant. So really, if you're substituting something in positive, you're just going to be looking in this first quadrant no matter which trig function it is. It's just the negative ones you have to be a little careful of. So if it's negative for the arc sine, arc tangent, arc cosecant, you're going to look between negative pi over 2 and 0. But if it's negative for arc cosine, arc cotangent, and arc secant, you're going to look between pi over 2 and pi in the second quadrant. Okay, so let's review how we evaluate some expressions here without using a calculator, these trig functions. There are different ways to think about it, but I'll show you what I think is the easiest way to probably figure these out with a calculator. So arc cotangent. Remember what these inverse trig functions do. They reverse what the original trig function does. So the original trig function takes an angle and gives you back a ratio of the sides of the triangle. That's one way of thinking about it. So here you can think of this as taking that ratio of the sides of the right triangle and giving you back the angle in radians. So this is not a fraction, it's like 1 over 1. And cotangent, remember, is the reciprocal of tangent. Tangent would be opposite over adjacent. So cotangent is adjacent over opposite. So let's try to draw that. In this case, it's positive, so we're just going to be looking at the first quadrant. We draw a right triangle, with the adjacent one and the opposite one, you can see that angle would be 45 degrees or pi over 4. So arc cotangent of 1 is equal to pi over 4. And again, what it's doing is reversing cotangent. Cotangent of pi over 4 will give you adjacent over opposite, will give you 1. So arc cotangent of 1 reverses that and gives you back pi over 4. All right, let's take a look at the next one. Arc cosine of negative 1. Yeah, it's not a fraction, so you can think of it over 1. Well, the original function, cosine, gives you the adjacent over the hypotenuse. So if we try to draw the triangle here, notice it's negative, and for arc cosine, that's going to be between pi over 2 and pi. So we try to draw our triangle here. Adjacent, negative 1, hypotenuse 1. So take a close look at that triangle. Something seem a little odd about that? Well, notice this is really an impossible triangle, right? Because the hypotenuse has to be the longest, the sides of the right triangle. So you cannot have a hypotenuse of 1 and then the adjacent here of 1 as well. So this is an impossible triangle. I'll cross it off here. And when that happens, that means you've got to be at one of these 4 points where you don't need to draw a triangle. In this case, where cosine is equal to negative 1 is right here. And that's just the angle pi. So it's kind of like a flattened triangle in a sense. So, since cosine of pi gives you negative 1, arc cosine of negative 1 will give you back pi. So if it's impossible to draw the triangle there, that means it's either at one of these 4 points or it's an undefined function and there's no answer to it. All right, now let's look at the arc sine of negative square root of 3 over 2. So think the original function sine takes the opposite over the hypotenuse. This one's already a fraction. And it's negative, so let's draw what that would look like. Well, for arc sine, when it's negative, remember for arc sine we have to look between negative pi over 2 and 0 in the fourth quadrant there. So the opposite is negative root 3, hypotenuse 2. You can see that's an angle of 60 degrees, but in this case we're going the negative direction, so it would be negative 60 or negative pi over 3. Again, the sine of negative pi over 3 would give you negative root 3 over 2. So arc sine of negative root 3 over 2 gives you back the angle of negative pi over 3. And finally, arc cosecant of square root of 2. Again, this is like square root of 2 over 1. Secant's a reciprocal of cosine. Cosine would be adjacent over hypotenuse. So secant is hypotenuse over adjacent. And it's positive, so we just look in the first quadrant. So if the hypotenuse is root 2 and the adjacent is 1, you can recognize that's the angle pi over 4. Again, secant of pi over 4 would give you radical 2. So arc secant of radical 2 gives you back pi over 4. All right, now let's take a look at applying calculus to finding the derivatives of these inverse trig functions. Before we do that, let's just remember there's two different ways of writing these inverse trig functions. Arc sine, or the sine with a little negative one, just like our regular inverse notation is written like this of an inverse function. Sometimes you'll see these inverse trig functions written this way. It means the exact same thing, just two different ways of writing it. Or arc tangent could be written this way. And this is usually the way you'll see it written on most scientific or graphing calculators. But you can see it written either way, just realize it's the same thing. So the derivative of arc sine of x is 1 over the square root of 1 minus x squared. The derivative of arc tangent is 1 over 1 plus x squared, and the derivative of arc secant is 1 over the absolute value of x times the square root of x squared minus 1. So they're all very similar. They all start with 1 over. Notice arc sine and arc secant are similar, except arc sine it's 1 minus x squared inside. Arc secant's the reverse, x squared minus 1. And arc tangent is the only one that doesn't have the square root on the denominator. So you want to make sure you have these memorized. There's 6 of them, but I'm going to argue that there's really, in a sense, only 3. If you just remember these, arc sine, arc tangent, and arc secant, notice the ones right here, the only difference are identical formulas, they're just negative. Right? And notice that they go together. Sine goes with cosine, tangent goes with cotangent, and secant goes with cosecant. So if you can memorize these three, then the cos are just the opposite sign of those, the corresponding ones. So let's look at some examples here using these new formulas. It says find the derivative of the function. So f prime of x here. Well, we've got arc sine, this formula here. However, notice it's not just x in there, it's 3x. So normally the derivative of arc sine would be 1 over square root of 1 minus x squared. But in this case, it's going to be 1 over the square root of 1 minus whatever's inside there, that's where what goes for x. In this case, it's x that gets squared. Here, it's going to be the 3x that gets squared. But since we're taking the derivative, when there's a function inside that's not just x, remember that also requires the chain rule, which means we have to multiply by its derivative, which is 3. And then if we simplify that, we get f prime of x is 3 over the square root of 1 minus, and if you square that out, that's 9x squared. All right, let's take a look at the next one here. On this one, we've got g of x equals this function. Notice these are added, so we can take the derivative of them separately. So g prime of x, well, here we've got the natural log of 1 plus x squared. This is a little review one. Again, it's not just x there. So there's the function inside, so this is going to require the chain rule. So remember, natural log of x, the derivative is just 1 over x. But in this case, it's going to be 1 over whatever's inside the natural log, which is 1 plus x squared. But again, using the chain rule, that requires us to multiply by the derivative of the inside. In this case, the derivative of the inside, the derivative of 1 is 0, derivative of x squared is 2x. And then plus the derivative of arc cotangent. Well, cotangent, all the ones that start with co, remember, are negative, so it's negative 1 over. And just like tangent, it's 1 plus x squared on the denominator. So then we've got 2x minus 1 all over 1 plus x squared. Since they have the same denominator, we can combine it to be a single fraction. Makes it a little simpler. Now let's take a look at this next one here. So here, since it's y equals, the derivative would be written as dy dx. We've got arc secant, but again, it's not just x. We've got x cubed inside there. So that's going to require the chain rule. And start on the outside. So normally the derivative of arc secant is the most complicated of these. It's 1 over the square root of x, or absolute value of x, times the square root of x squared minus 1. That's if it's just x though. In this case, the x is there and there, so that's where the x cubed is going to go. So it's going to be 1 over absolute value of x cubed times the square root of x cubed squared minus 1. But again, using the chain rule, there's a function inside that requires us to multiply by the derivative of the function inside, which is 3x squared. So if we start to simplify that, we get 3x squared over absolute value of x cubed times the square root. X cubed squared, you multiply the exponents, so it's x to the 6th minus 1. Then you might wonder, well, could that be any simpler there? Well, we've got x squared and x cubed. Can we just reduce those like we normally would, or does that absolute value make a difference? Well, let's take a look at that absolute value of x cubed. Well, with absolute value of x cubed, couldn't we write it as the absolute value of x squared times x? We split it out that way. It's the same as x cubed, right? And then look at that. X squared will never be negative. So that absolute value will never affect the x squared. So the x squared you can actually pull outside the absolute value. But then the x could still be affected by the absolute value because that could be negative. So really it would simplify to be this. And if we simplify it to be x squared times the absolute value of x. Then you can see those x squareds, now that it's outside the absolute value, can actually reduce out. So our final simplified answer would be 3 over absolute value of x, the square root of x to the 6th minus 1. All right, now let's take a look at a couple tangent line problems. So this one says find the line tangent to the function of a given x value. So remember, for the tangent line, there's two things we need, the point of tangency and the slope. So let's find the point of tangency first by just substituting in the -1 and for x. Okay. So -1 squared, that's just 1. And then arc tangent of -1, well, that's the opposite over adjacent. So if we draw that off to the side here, remember arc tangent, when it's negative, we look in the fourth quadrant here. So if the opposite's -1, adjacent's 1, you can see that's the angle -π/4. So it's 1 times -π/4 gives you -π/4. So there's your y coordinate. So now we know -1, -π/4, that's our point of tangency. All right, now we need the slope of the tangent line. And remember, the slope comes from the derivative. It gives you the slope of the tangent line of the function. So if we've got this function, we want to take the derivative. Notice what rule we have to use overall there. We've got x squared times arc tangent of x. So you have to use the product rule on that. And then multiply the other. So remember the pattern of the product rule. You take the derivative of the first one, root of x squared is 2x, times the second one as it is, plus the first one as it is, x squared, times the derivative of the second one, which is 1 over 1 plus x squared. And there's not too much to simplify here. So actually, let's go ahead and just substitute in the -1 right now. So there's not much to simplify. So this would be 2 times -1, arc tangent of -1, plus, this is x squared goes in the numerator, -1 squared over 1 plus -1 squared. Now we just need to simplify it. So we have -2 there. Arc tangent of -1, remember we already evaluated that to be -π/4. So that's still going to be -π/4 there. And plus, that's going to be -1 squared is 1 over, that's 1 plus -1 squared is 1. 1 plus 1 gives you the 2. And if we simplify that, f prime of -1, the negatives and the 2 are reduced into the 4, so that would just be π/2 plus 1 over 2. Since they already have a common number, you might want to combine that to be pi plus 1 over 2. So there's your slope of your tangent line. So then the tangent line will just be y minus -π/4, makes it y plus π/4, equals the slope we just figured out, pi plus 1 over 2, times x minus the x coordinate, which was -1, makes it x plus 1. All right, let's take a look at one more tangent line problem. So we've got the arc cosine of e to the 2x at x equals 0. So let's first find the point of tangency by substituting 0. So arc cosine of e to the 0. But e to the 0, anything other than 0 to the 0 power, is 1. So that's arc cosine of 1. And cosine is the adjacent over the hypotenuse. It's positive, so we look in the first quadrant. If Make the adjacent one hypotenuse 1. Notice again there's an impossible triangle there. So if this answer exists, must be at one of the 4 points right there. If you are looking in the first quadrant, just think, well, where is cosine equal to 1? That'd be right there, right? At the angle of 0. So our cosine of 1 is just 0. So your point of tangency is just 0, 0, right at the origin. And then to get the slope, that comes from the derivative. Notice here, got a function inside, e to the 2x, and a function inside that 2x. So this is the double chain rule for the derivative. So start on the outside. Derivative arc cosine. It starts with a co, so it's negative 1 over. Normally it's the square root of 1 minus x squared. But here what's inside there is e to the 2x. So it'd be e to the 2x squared. And then using the chain rule times the derivative of e to the 2x. That e stays the same, just like e to the x does, but we also need the derivative, the function inside that, derivative of 2x is 2. So if we simplify that, that's going to be the derivative is negative 2 e to the 2x over the square root of 1 minus e to the 4x. We multiply the exponents 2x times 2. Then we can substitute in our point of tangency, which was at x equals 0. So that'd be negative 2 e to the 0 over the square root of 1 minus e to the 0. Well, e to the 0 is just 1, so that's negative 2 over the square root of 1 minus 1, but that's the square root of 0, which is 0, so you get negative 2 over 0. Well, that's undefined. So, undefined tangent line, remember the vertical tangent line there? So a vertical tangent line, it's got to be x equals, and in order to go through the point of tangency, it'd have to be x equals, the x coordinate right there is 0. So there's a special case for the tangent line. That concludes the notes for AP Calculus on the topic of inverse trig functions and differentiation.